This section connects the coordinate systems of analytic geometry back to vector spaces. Coordinates let us treat lines and planes in vector terms, and the geometry repays us in intuition about vector spaces. We begin by reviewing how the correspondence is set up. Start with a line. Choose on it a 0 point and a distinct unit point. Then each point gets a number. Its size is the distance from the 0 point, measured in units of the segment to the unit point, and its sign says which side it lies on. 3 dimensions go the same way. Choose an origin and 3 unit points, the 4 not lying in a plane. Each unit point determines a line through the origin, and these 3 are the coordinate axes, each already carrying a correspondence of the kind just described. Now take any point of space. The plane through it parallel to the second and third axis meets the first axis, giving the first coordinate. The same construction gives the other 2. So every point determines a triple, and that is the correspondence defined by the axis system. Worth noticing, the coordinate triples of the 3 unit points are exactly the vectors with a single 1 and zeros elsewhere. That fact gets used again and again shortly. There are 4 basic facts about the correspondence. Strictly, they must be proved as geometry before coordinates can be used on geometric questions. But the book calls them tricky and almost impossible to discuss on the usual school treatment, so it simply assumes them. First, the correspondence is a bijection from space onto coordinate 3 space. Second, 2 segments are equal in length, parallel, and similarly directed exactly when endpoint minus starting coordinates agree. Formalized, that says the 2 directed segments are equivalent. Third, if a point is not the origin, then another point lies on the line through the origin, and it exactly when the second set of coordinates is a scalar multiple of the first. Moreover, that scalar is the coordinate of the second point on that line, taking the first as its unit point. The fourth assumes the axes are Cartesian, mutually perpendicular, with a common unit of distance. Then the length of a segment from the origin is the Euclidean norm, the square root of the sum of the squared coordinates. This follows directly from the Pythagorean theorem. Applying Pythagoras again to the triangle on the origin and 2 points gives another fact. 2 segments from the origin are perpendicular exactly when the scalar product of their coordinates is 0, that product being corresponding coordinates multiplied and summed. One more property is useful. Hold either variable of the scalar product fixed, and it is linear in the other. Then the equation of a line drops out. The line through a point parallel to a direction contains a point exactly when the coordinate difference is a multiple of that direction.